Everybody, I'm Samuel De Guido, Planning Manager for the Institute of Digital Engineering UK, and I will be facilitator of this webinar today. Welcome to the OPTIMA webinar. This is the first of a series of 3 webinars on digitalization, the art of the possible, organized by the Institute of Digital Engineering. The series will showcase the 3 proof of concept projects funded by IDE on the opportunities that digitalization gives and offers to improve product and service through the whole life cycle. Before going into the details of the OPTIMA projects, I would just like to remind you a couple of housekeeping rules. As a default, your microphone and cameras are off. You might have the opportunity to have your microphone on towards the end of the session after the presentation in the Q&A session. The Q&A, there is a Q&A box at the bottom of your screen to submit your questions. So please do this whilst the presenter are presenting their work. Today's webinar is also being recorded, and recordings will be available through the IDE website on the OPTIMA project page. There's a chat box functionality. This can be used to interact with the other people, with the other attendees, as well as asking technical assistance. My colleague Sunny will be help you there. And last but not least, we have a feedback form through Mentimeter survey at the end of the webinar. So when the webinar ends, please, I would be highly appreciated if you could fill in your feedback. Today's webinar, back to the content of the webinar. OPTIMA aimed at creating a link between existing softwares and allowing to extend the optimization of composite materials into the non-linear type of analysis. This then will enable engineers to have a more robust solution when designing composite materials. And this is also very much aligned to the IDE purpose, as well as to the recently launched IDE digitalization roadmap, which happened in March this year. This has been launched by IDE, and in particular, this project tackles elements around interoperability, in particular within software, optimization, and enhancement of modeling and simulation, which effectively are key elements of our roadmap. With me today, I have Martin Gambling, Managing Director of GRM Consulting, James Witt, who is head of Final Element Tools and Tool Strategy at Red Bull Advanced Technologies, and Robert Hansen, who is head of Structural Design at McLaren. They worked on the OPTIMA project, and they will go through the elements and the results of the project itself. So without any further ado, I would like to give the floor to Martin to explain the content of the projects and the results of it. Martin, over to you.
Wonderful. Thanks, Sam. And good morning to everybody. Hope you can all hear me. Sam, do let me know if I'm talking with the mute button on.
No, I can hear you.
Brilliant. That's great. Okay, I shall just share my screen. Just one moment. And then we are good to go. Okay, so hopefully all of you can see that. Yes, thanks for the introduction, Sam. So myself, Jamie, and Rob will be giving you an introduction over the next 45 minutes, 50 minutes or so about the OPTIMA project. So I'll start by giving an introduction to the overall project objective, and then Jamie and Rob will give an introduction to themselves, their teams and companies, so Red Bull Advanced Technologies and McLaren Group. And they'll discuss their motivations for getting involved in the project and how they've helped. Then it'll return to myself, and I'll talk a little bit about the technical aspects of the project, not in too much depth today. I don't want to bore you all with that, but about the technical approach, how it's worked, and how really we feel it fits so strongly the use of optimization technology with composite materials. We'll discuss some of the applications and possible future applications that we see that are really a great use case for the tools and the methods developed. And then we'll look at the direct outputs we've achieved in this IDE project before wrapping up. Okay, so first of all, on to the introductions. So in terms of the project itself, so Project OPTIMA was a collaborative project of 3 partners, so ourselves, GRM as the lead partner, and then McLaren Racing and Red Bull Advanced Technologies as the collaborative partners. So our role as the lead in this project was to run it, to manage it, and to develop and plan the methods that have been created throughout the OPTIMA project, and then the software development, actually implementing those. And then we do our own testing, and then that's where the work with the partners really comes into its own and gives strength to the project. So having McLaren and Red Bull on board, they were able to give us the project definitions and requirements that they needed from a tool to make it relevant to how they work and develop their structures in the digital world. And with that, they're able to give us real world industry examples that we could test the tools on and make sure we are answering the right questions with the technology. And the main focus, the drive of what we're trying to achieve, so the objective of the project, is to implement a coupled process of using the optimization technologies we have at GRM and have developed over the years, and coupling those to the Abacus nonlinear solver. So it's really providing that integrated solution and that step forward in the level of capability by being able to solve in that nonlinear domain. So the output is this new digital product to improve the structural engineering process for composite materials. So just to very quickly highlight that process. So on the left, we've got a very bendy aero wing. So as you can see here, this is from Abacus. So we have that very large nonlinear displacement factor in Abacus. That's the solving we're looking to work with. And then on the right, we're trying to couple that to the OptiAssist composite optimization technology, where we can develop ply shapes, as you'll see a little bit later, and develop and optimize your laminates for many hundreds of thousands of design variables. So it's bringing that technology together. A key thing about OPTIMA from an overall project point of view is it was a very short and very focused project. So only 3 months. We started it just at the very end of December last year, and it ran through till the end of March. As you see, the timings there are very tight, and that presented both challenges to get things done and a lot of opportunities in how we worked as a collaborative team, and that was really, really good. So in terms of how we did that, and the benefits of that is because it was such a short project to achieve a lot, to deliver this technology in terms of the methods and then the project from it, is we had to work with a very much an agile project structure. So we kicked off as partners with the initial planning and specifications, and then we went into a sprint cycle, a 2-week sprint cycle, where we were all as partners meeting every 2 weeks. We were doing our developments, and then those would roll out to the partners, Red Bull and McLaren, who could then do their testing, provide their feedback, and keep that in the process. And it's really key, as you can imagine, with only 3 months to deliver this project, you couldn't go, well, I'll catch up with them next week. It really kept that communication level at a great high tempo level. Okay, so that's just an introduction. We'll go back into a lot more detail of the project after some introductions and motivations from our partners. I'll start off by introducing Jamie Wheat, who is the head of FEA tools and tools strategy at Red Bull Technology. So Jamie, I will just give you control of mouse keyboard. Hopefully you can come off mute and take control.
Works flawlessly. Yeah, so I'm going to give you a bit of an introduction into Red Bull Advanced Technologies. So the history of us, Red Bull Advanced Technologies was set up in 2014, and The principal aim was to exploit F1 technology and design processes on commercial and very much non-F1 related projects. By 2015, this had become a fully fledged design consultancy, offering services that include pretty much all the design and development areas that help to produce an F1 racing car. In its short history, we've worked on many high-profile projects, and I have some details of some of those projects on the following slides. The organisation has also grown over the few years that it's existed and does now encompass more experience from other motorsport categories and also from the automotive sector and more recently EV sectors. On the previous slide, I talked a little bit about the design areas that help to produce an F1 car, and this slide just highlights some of those areas in a bit more detail and the services that we can offer. It's worth noting that vehicle doesn't necessarily always mean car, and that's something that's illustrated in the examples of projects that I've got to talk about. We're very much set out to be optimization led, whether that's a mechanical design, a composite design, or something that's aerodynamically driven. But that also expands into tools and software and the mathematical modeling that we undertake. So that brings me on to the sort of vehicle science teams who offer many vital services within the F1 design process. And these can also be exploited for development on RBAC projects, whether that's driver in the loop simulator work, optimization of control systems, integration of systems into other tools or products, or leveraging the F1 tyre model development that goes into understanding the F1 tyres. At the top of the tree really is the aerodynamic process, and being able to offer a fully optimized F1 CFD workflow is something that helps differentiate us from other consultancies, and that clearly includes the creative approach that F1 aerodynamicists have to take to succeed within F1. The RBAC facility is very much a dedicated building, but it also sits within the Red Bull Racing Technology Campus in Milton Keynes. And that campus is something that's expanded a fair amount over the recent few years. Having all the business entities of Red Bull Racing, Red Bull Technology, Red Bull Advanced Technologies, and most recently Red Bull Powertrains co-located does allow us to share talent, processes, facilities amongst the group to operate more efficiently. Offering unique access to cutting-edge facilities is also something that helps differentiate us. There's not many places where you can go and use F1 standard design in the driver in the loop simulators, for example, but it also extends to things like R&D test facilities. If we look even wider, Red Bull has global exposure, not only operating motorsport teams, but also touching other sports such as football, and more recently expansions into esports. We work with and support a lot of athletes to help them not only understand but also optimize and improve their own performances in whatever disciplines or activities they compete in. We participate in engineering and technological events. The F1 show car, for example, operates in many different countries around the world, and also in many different environments such as snow-top mountains or sandy deserts. The Felix Baumgartner event, as you can see in the image, was something that we were involved in, and more recently you may have seen videos of the Zero Gravity Pit Stop Challenge. The key running theme for us is that Red Bull as a whole is always trying to push the boundaries and doing things that others may not dare to do. The F1 car on the top of the helipad is a good example of this. Not many people would think it's probably a sane thing to do. But this demonstrates the Red Bull ethos of being high energy and high octane, that mentality. So onto some examples of work. It's worth pointing out that in each of these projects, it illustrates very well how we work. It's generally about delivering digital solutions, and we will use the manufacturing talent within the client's capabilities or engage with a manufacturing partner to deliver the physical products. So the first project is probably the most famous, and that's the Valkyrie. This was working with an automotive partner to deliver the world's fastest, most innovative road car. A road car that you could literally drive anywhere in the world to a racetrack, drive around that racetrack, smash the track record, and then drive home again. It was about putting F1 technology and development on the road, adapting the F1 aerodynamics design process to deliver a road car that has more downforce than current F1 cars, and implementing technology that you would like to implement on F1 if you were allowed to do so. It's a bit of a stretch just with the price point of 2 million, but it was also about giving the opportunity of others to experience F1 performance and not just the 20 lucky F1 drivers each year. Second project was working with Ben Ainsley Racing. So Ben Ainsley approached RBAT with the desire to work with Adrian on a project, strongly in the belief that they could deliver something that would improve the performance of the yacht and give him a competitive advantage when racing. So this project was very much about digitally enabling technology. And it was split into two sections. The first was to provide a tool and methodology to help them examine global effects of design changes. So dagger boards would be a good example of this. Not only just looking at the performance of that design change in isolation, but how does it change over the entire race? What's the global effect? And secondly, it was about adapting the philosophy of the strategy tools that we use at race weekends to work out when we should be changing tyres and what tyres we should be on, when we should be pitting and things like that. Applying that to a completely different environment with different inputs, different outputs, and adapting it to deliver tools that they could use for pre-race course optimization and be fully integrated within their existing tools and procedures. The third example is yet another different type of vehicle, this time an aircraft. And it was the aircraft used in the Red Bull Air Race. Again, this was split into a couple of packages of work. The first being adapting the processes and procedures and analysis techniques that we use to help design F1 chassis and applying that to the pilot survival cell to help make it a safer environment for the pilot. And then secondly, it was to look at redesigns of the aircraft to aid the show and improve the entertainment aspects. So could we make the aircraft more agile? Could we make it faster? Could we make it handle better? But it also stretched into aesthetic changes to make it more dramatic for spectators. So an example of that was using air jets on the wingtips to create vapor vortices. Something that doesn't necessarily help performance, but it helps create a better experience for spectators. And the final project was something that we worked on with IndyCar on their driver protection system. So IndyCar really wanted a full aero screen for their driver protection. They'd already had a couple of attempts and for one reason or another hadn't managed to deliver something successfully. But this was something that was on their roadmap. They promised it to teams and drivers. The only problem they had now was that time was tight. So we worked with them to understand the performance criteria, but also other aspects that were critical to the design. For example, it needed to be retrofitted to current chassis. IndyCar differ from F1 in the fact that they don't change their chassis designs year on year. So it was very important that it had to be retrofitted to current chassis. From the start of the design process to delivering something that successfully passed testing took about 5 months, and it's something that they currently use in the sport now. So just to finish off, I want to try and make the link between the projects I've just talked about, simulation and OPTIMA. So projects for me generally come down to the 3 constraints of cost, time, and performance. And if you imagine that there are the points of an equilateral triangle, you can draw a dot in the center, and that could represent a perfectly executed project to the exact targets that you set out. Now, perfect delivery of projects doesn't really happen, and something will always change to move those different criteria. So the way that you cope with this is you draw a circle around that dot, and that represents the tolerance or scope creep that you can accept and still deem it to be a successful project. The size of that circle is based upon things like the tools you have, the resource you have available, the experience that you have on delivering similar projects before. And this is where simulation comes in. So the more simulation that you can do, the better understanding you will have, and that will lead to greater confidence in project delivery. And all these things allow you to have a smaller diameter on the circle and therefore a tighter tolerance on the project constraints. So OPTIMA is going to help us with that, because right now the composite optimization workflow is not as streamlined as we would like it. It sits outside the principal structural designer procedures. So OPTIMA will change that by bringing it into the same workflow. Therefore, we can use composite optimization techniques more frequently on more projects. That should decrease the amount of time needed for simulation and therefore help us deliver better designs. We feel that the pace of working within RBAT and F1 especially has helped on this project and should contribute to a more robust and mature project at the end of the day. That's it from me, Martin, if you want to take control again.
Okay, I'm back. That's good. Thanks, Jamie. Much appreciated for that. It's a good intro to Red Bull Advanced Technologies and why you kindly got involved. So next, I'd like to introduce Rob Hansen. So Rob Hansen is the head of structural design at McLaren Racing, and so give us a bit of an introduction to McLaren as a group, and again discuss why he's got involved in the project. So there we go. I can see he's appearing on screen. So over to you. Actually, I'll just give you control as well. So,
thanks, Martin. Hello, everyone. So I'll start by introducing McLaren Group. If I can move to the next slide. So McLaren is well known globally as one of the most illustrious high technology brands. The group's built on its successful racing expertise and diversified to include a leading performance car, sports car business, McLaren Automotive, and more recently a technology and innovation business, McLaren Applied. All three McLaren companies are based at the McLaren Technology Centre, the MTC in Woking, which has been our global headquarters since 2004 and has extensive design, production, and test facilities all under one roof. Our car brand, McLaren Automotive, is leading creator of luxury high-performance sports cars and supercars. Every vehicle is hand-assembled at the McLaren Production Centre, the MPC, which is on the same site as our McLaren Technology Centre in Woking. Our technology brand, McLaren Applied, works to harness our technology, data, and ingenuity to deliver performance advances in industries as diverse as health, public transport, and energy. The company primarily offers solutions in telemetry, control and analytics, electrification, and virtual product development, all activities that are directly descending from our Formula One activities. But McLaren Racing is at the core of what we're about and where it all started. In 1963, Bruce McLaren founded the Bruce McLaren Racing Team. We contested our first Formula One race in 1966, winning our first Grand Prix in Belgium in 1968. And 53 years later, we have 182 Grand Prix victories and 20 World Championships. Although F1 remains at our core, we've recently started a new chapter with our IndyCar team and in esports with the McLaren Shadow project. McLaren has a strong racing pedigree. We're the only team to win Formula One, IndyCar, Can-Am, and Le Mans championships. McLaren also has a rich heritage of ambition and innovation. When McLaren Racing, as we know it today, was formed in 1980, it pioneered the first full carbon fiber monocoque chassis in Formula One with the MP41. Our sister companies, McLaren Automotive and Electronic Systems, were formed in 1989. The McLaren F1 road car, one of the most iconic road cars of all time, was born in 1992 and later became the world's fastest production road car. It also won on its debut at Le Mans 24-hour race, which was particularly impressive as it was a road car first and foremost. McLaren Applied was formed in 2004 and later became an exclusive supplier of standard engine control units to IndyCar, F1, and more recently even NASCAR. But in 2010, things started to kick off, and McLaren Automotive became an independent entity. And in 2011, the McLaren Production Centre opened, which is where every McLaren road car is now assembled. Over the past 9 years, McLaren has grown into a major player in the high-performance road car sector, having delivered its 20,000th production road car in 2019. So I'm going to talk briefly about why simulation is important to engineer designs in Formula One. Anyone familiar with Formula One will know it's a highly competitive environment. Timescales are extremely tight. From initial car concept right through to the launch of the car, there are only between 6 and 12 months, with only 3 days of prescribed track testing allowed before the first race of the season. It's critical that every element of the car is delivered on time and working to its full potential straight out of the box. But even after the car is launched, it's continuously evolving. By the time the car hits the track for the first time, the next update will already be in production. By the end of the season, almost every part that you can see on the outside of the car will have changed in some way or form. So being able to test, iterate, and advance our designs quickly in aerodynamics and mechanical design is critical to success. Formula One is a development race foremost. So if we look at aerodynamic devices specifically, despite the quite restrictive regulations, the thousands of new geometries are evaluated every single month. Some of these are tweaks of existing designs, but many are major concept changes or a reflection of new ways of thinking, or philosophy, as many in the industry call it. And simulation is a critical part in our ability to rapidly develop a competitive car, and also to understand how things interact. Whether it's CFD for modeling the airflow around the car in detail, so computational fluid dynamics, that is, finite element analysis, FEA for structural integrity, stiffness, weight efficiency, or multi-body simulation, MBS, for complex multi-body, complex dynamic interactions, multidiscipline or multi-physics simulations to capture things like fluid structure interactions or thermal interactions, and systems and control and mechanical systems modeling to allow us to model complex control and mechanical system and their interactions with the rest of the car. There's obviously other model simulation that's carried out, but these are kind of the most prolific ones. And all these are vital in their own right, but they also feed into our lap time and driver in the loop simulations, which help steer the development of the car and basically ensure that we're able to make the best engineering decisions. Optimization technology is intertwined with all these types of simulation, enabling us to home in on the optimum solutions as quickly as possible. All this is even more important as we negotiate the rule changes for the 2022 season. That these are designed to improve overtaking and are the biggest change in F1 for many years. There is no reference point or existing track data to benchmark against, which means that in order to be competitive, we will need to draw on all our learning from recent years to ensure that our modeling environments are as effective as possible. With tight limits on CFD and wind tunnel testing built into the regulations and a strict cost cap limiting development, fast and accurate simulations will be the key. So why did we decide to support OPTIMA? Well, McLaren Racing has been utilizing FEA technology to help us design light and efficient composite structures for over 15 years. However, the time and overhead and expertise required to incorporate composite optimization into existing workflows has often made it quite inaccessible for some projects. The limited ability to consider nonlinear effects when optimizing composites has also meant that some projects have not been able to benefit fully from this capability. We felt that this was a great opportunity to influence and contribute to the development of a tool that could really address some of these limitations. In future, this technology will enable us to incorporate composite optimization into many more composite structural components, analysis workflows, which should lead to lighter, more structurally efficient designs and allow us to do this more quickly and therefore potentially produce a faster car. Okay, thanks for listening, everyone. It was quite a short overview, but I hope you found it interesting. Now I'll hand over to you, Martin.
Okay, great. I'm back. Thanks for that, Rob. Thanks to both of you for those presentations. It's good to see the introduction. And I think from both of them, you can really see the amount of simulations going on and then the drive to just really enhance and add new processes into that simulation design approach is key. And that's really what OPTIMA's all about. Okay, so we'll delve back into OPTIMA itself a little bit now and the details. So as part of that, we really should look at the fit with composite materials and optimization. It's something that when you start looking at it, you realize it's such a strong fit for how the processes can be developed. Now, some of you on the call may be very, very familiar with composites. So this slide is really not so necessary, but if you're new to composites or you're not really sure what is the definition of a composite, well, quite simply, it's the mixture of two or more materials together to create this resulting material that you work with, and that is in generally done with the purpose of creating superior material properties. And so, really, that's what we're working with. And there's sort of two parts to these materials that we're looking at typically. So you've got your matrix material, which is a resin. So it might be a polyester, epoxy, or phenolic, some material that binds everything together. And then you've got the fibers themselves. Oh, hold on. I just need to stop Rob from controlling my mouse. Obviously. Thank you, Rob. And then we've got the fibers. So these are the materials that typically are giving the enhanced material properties. So this could be carbon fiber, either a chop strand or a long fiber, where we can control its orientation and position. Equally the same for glass and aramids and other materials. So these fiber materials are the ones that really offer the stiffness, and basically they also allow that tuning of the material properties. So you can see that if you have more or less of certain fibers in different directions, you can control the stiffness, tune the stiffness and the strength of a structure. And that really can give you that really efficient material. So you're really maximizing the potential of the composite materials. And the number of possible combinations really just explodes into huge amounts, really. And here, we can have easily hundreds of thousands of possible combinations of fiber placements, fiber orientations, different fiber types. And so to do that by hand, yes, it's possible. You can do that. And, there are very experienced and capable composite engineers at the likes of Red Bull and McLaren that are doing this. But if you go beyond that, or you combine that with optimization technology, where the methods that we have developed and continue to develop through projects such as OPTIMA, they can consider into the hundreds of thousands of variables and that fits so well with what you can achieve with composites. So you can really exploit the flexibility of your composite material. So the benefits in terms of the real world, well, by maximizing that material potential, you can develop better laminates, and you can do it quickly, more quickly, and making the most of the composite materials. And the key thing is, when you're looking at using simulation, the first step of simulation is to go from assessing something in the real world through testing to simulating it. And that's that virtual test. I assess something, does it work? But if I want to iterate it, then I make a change to it. I do another virtual test. That is what simulation does. But through optimization, you can free up the engineer and reduce that manual iteration time. So very easily you can say, well, these are the things I want to change. These are my targets. You do the iteration for me. That's really a key thing. And in doing that, you can start to identify designs that meet multiple requirements. And that's where the strength of optimization really comes into its own as well. Great engineers can consider 1, maybe 2 load cases and their trade-off. But when you've got maybe 10, 20 load cases for stiffness, strength, vibration, buckling, heat transfer, all these different attributes, that's where getting an algorithm to consider that for you is really key. And so taking advantage of all that, you're reducing material usage, and that either leads to part cost or mass improvements or performance improvements, depending on what your motivation is in what industry you're working in. And of course, because we can take out that iteration step, we can present a certain optimization formulation and put that to multiple different design concepts. They may be different aero concepts in Formula One, or different geometry concepts for other designs, and you can then run them through the optimization and then perform that trade-off and feasibility study to see which is the best. And the key thing really is what we're doing in OPTIMA is we're coupling these technologies to Abacus, and Abacus being this very advanced, very mature, nonlinear solver is able to consider simulations much closer to the physical behavior of parts, and so closer to reality with your digital simulations. So in terms of the technical summary, I don't want to delve in too deep and lose you all with boring optimization geekery, but just to basically go through the flow of what's happening. And we'll do it here on this simple box to explain the principle first of all. So if we look at our Abacus simulation, we start with this, and then we've got this workflow, and we see highlighted in red is this looping, and that's to manage the nonlinearity that we see in the real world sometimes. But we're going to take an Abacus model. So here we've got a box section. It's under a bending load case that you can see in the bottom right. It's bending a great big 51 millimeters at this moment. And what we've done in this is we've put some woven cloth fibers at 0 degrees and at 45 degrees. And that's just uniformly over the structure. And so we know we need to add fibers to get this displacement down. And we want to get down to a target of 5 millimeters. That's our test case we're going to demonstrate here. So we want to know where's the best place to add more fibers, and how many do we need? So the optimizer will then be called upon after the data conversion and management, and we end up for each of our different fibers. So here we're looking at our 0s and our 45 and their placement on the top surfaces, bottom surfaces, and the sides. And you can see, hopefully, taking this simple case that's something that our engineering brains can accommodate very easily. You can see under bending, it wants the most material on the top and bottom surfaces, and it wants the 0 degree material where the strength runs along the length in the more efficient manner. And so you can see we've got great more thickness at the root and less at the tip. So that's something that intuitively we can see. And so the optimization process does that solving, and then updates the Abacus model and reruns the simulation to verify that performance. And say if there is nonlinearity, we then loop until we manage a level of convergence in that solution. So you can see here we're at the target, and here you can see how the plies for the composite structure have been realized into different ply shapes as we go. So other applications in the world of Formula One, we've got a nice generic one. I would love to have shown you some of the real world examples from the likes of McLaren, but as you can imagine, they're not keen to share those on the screen. Very sensible. But here's just generically, we've got the kind of example where we've got different stiffness requirements for forward and rearward loading. And additionally, we want to maybe tune and tailor the stiffness for other requirements such as aero as well. And so here we've placed what we describe as candidate fibers of UD fibers along the length of the wing, some cloth at different orientations as well. And you can see this, we've actually allowed it to go into a fair amount of fidelity. Sometimes you don't go as complex as that, you want to simplify your structure. But you can see where it wants the main run of thickness. As we see here, these colors are showing thickness of the UD fibers along the length. And actually, it's then introduced some woven plies at 45, where we've tried to allow it to tailor stiffness to manage rotations if we wanted to in the design. Beyond motorsport, aerostructures are equally a huge application for this technology. What I didn't realize until I went through the years and learned about composites is when aircraft manufacturers start making airplanes out of carbon fiber, there's a sudden very, very high demand for raw materials because they're really big. And that's something you realize is how much quantity of material is used. So using the same optimization technology there, small percentage gains on an aerostructure can provide massive savings for raw material usage of the carbon fibers. And so here you can see a similar example of the application, focusing here on the placement of fibers, UD fibers, along the length where they're given the maximum strength. And you can see they're very much tapered thickness. The wing is like a cantilever, but with additional reinforcement at the engine attachment region. So in terms of further applications of the technology, you can see here, so automotive body, McLaren Automotive, a clear example, and other manufacturers who are producing their bodies from carbon, or even using carbon as a reinforcement of their existing metallic structures. The applications are very significant. All through motorsport and aerospace, and in marine, where again there's a sort of high consumption of composite materials, be they carbon or glass or others. And then importantly at the moment, renewable energies. So applications such as wind turbine blades that are predominantly composite in their construction. Okay. So what are the outputs of the OPTIMA project? And what are we going to do next? So the key output, the very clear one, is a new product, which is OptiAssist for Abacus. So this is delivering the optimization for laminate optimization and ply shape optimization of composites, all working directly with the Abacus solver. But that's really a foundation, I think, for the future as well. It's there for composites because the fit is so complementary, but it can go beyond that, and it's certainly our intention to take the successes of OPTIMA and move them on with our own developments for non-composite applications. So the same technology, the same methodology, so that Abacus users can take advantage of the technology for metallics, plastics, and other applications. And then thinking really about the future, this platform of how we've coupled the technology to the Abacus solver, the mathematics that we've developed for that approach and applied for that approach. There's nothing that really can't stop us from taking that beyond just FEA and incorporating other solvers and other solver methods into that process. That's something we're excited to investigate in the future, so we can really bring in the wider attributes of vehicles and engineering systems within the optimization loop. And that's really exciting for the future. Okay, so I will now just summarize where we've got to. If we take a look at the OPTIMA project, what have we achieved? I think the first thing we've done is we've developed this new software technology for developing composite structures. And importantly, that's delivered into an integrated solution for partners, Red Bull and McLaren. So it's within the tool sets that they use, they can incorporate it in a seamless fashion. And of course, if you're using similar tools, well, that's there for yourselves as well. Secondly, I've just got to say a huge thank you at this moment to my team at GRM and Jamie and Rob and their teams at both Red Bull and McLaren, because what we achieved in 3 months was really impressive. There was a moment halfway through where we thought, oh my God, are we going to do this? And it was through keeping that communication, recognizing when certain tasks couldn't be achieved. You know, there are limits to what could be done in a finite time ago, but those will be pushed out. We'll focus on them later, and then but maintaining the core part of the business, the core part of the project, I should say, throughout that 3-month period, and that was we consider a fantastic success. And we think we've pushed the boundaries a bit, really. So composite technology, composite optimization is not new. We're very much part of the world of people developing and applying technologies for composite optimization, but taking it that step on into coupling with Abacus and the nonlinear loading regimes that it can consider is a really good progression in what we're achieving for the world of simulation. And that in itself is that platform for the future. So nonlinear optimization, we can take beyond this and see what else is possible through the world of digital engineering. So thank you very much for attending. I think after this short video finishes, I couldn't resist sharing it, one of my favorites. We'll be going into a Q&A, so any questions can be answered. But thank you very much. And yes, back to yourself, Sunny.
Thank you, Martin, Rob, and Jamie for giving an overview. It's very interesting, actually, not only because in my past life of engineer I was working with composite optimization, finite learning analysis, but also because what you mentioned around the fast pace and the agile methodology that you've been able effectively to deploy into any engineering type of development has given very good results at this stage. So it was a very good demonstration how to apply also different way of approach to engineering. As you said, Martin, there's a Q&A session. We have a couple of questions from people that are happy to come live. I think the first one is from Navin Manhavan. Navin, are you there? I think he is.
Hello, can you hear me?
Navin, yes, we can.
Hi, brilliant. Hi, guys. Great presentation, great project, and it's very interesting. Certainly, you know, with the fast pace that you mentioned as well, not just within the project, but within what you guys do on a day-to-day basis. But I suppose one thing that I'm keen to understand, and with the data that you collect, obviously, you know, with the F1 sort of type of work that you do as well, how do you build and integrate the data science and machine learning models with your physics-based tools? Do you do that? Are they seamlessly integrated? And is there any benefit from that sort of integration?
So good question on the details. I like that, going straight into the technical part of it. So part of the key of how the processes work, we need to get that machine learning, that knowledge of how the structures are behaving into the optimizers. So there's a process we use. It's a process called the equivalent static load method, and what we are able to do is actually integrate the nonlinear solving from Abacus, and then we couple that to the optimizer, and that's using a gradient calculation that gets that knowledge and machine learning into the process. So in terms of how we integrate that knowledge into other solvers, the key challenge in all cases for this successful optimization and machine learning processes is to work out how to get those gradients. For this coupling we've done in OPTIMA, we have a process, this ESL process we use, but we have similar technologies and logics for different sciences, be it CFD, multi-body dynamics, and so on. But each application is subtly different in how it's done.
Brilliant, thanks.
Thank you, Martin. Jamie and Robert, do you want to add anything on that one, or are you happy?
I'm happy with that answer.
Thank you.
Playing the cards close to your chest.
They will definitely. I'll talk about it loads more on the consultancy. These guys, I know how to do this.
I mean,
I'm saying
all I can say, all I can say really is that there are a lot of the optimization tools that are used kind of widely in our industry will kind of benefit from things like genetic algorithms and those kind of approaches. Obviously, AI is the kind of, and machine learning are the sort of topics of the moment, and of course we're always trying to look for ways to exploit them and gain as much benefit as possible. But yeah, I think that's about all I can say on it.
That's fair. Thank you, Robert.
Brilliant. No, that's great. Thanks very much, guys.
And thank you, Navin. We also have another question from Alan Thomas, who's actually happy as well to ask the question himself. Alan, over to you. Sanis, Alan.
Here he comes. There's somebody busy behind the scenes getting all this sorted for us, Sam.
Indeed. Thank you.
Can you hear me?
Yes. Thank you.
I'm from the other end of the automotive business, mainstream production. So my question is it possible to consider practical manufacturing feasibility in the optimization? Because your industries are very carefully organized to do things very precisely, 1 or 2 times, maybe 5 or 6 times. Can you do that implicitly, or do you need to devise explicit constraints, or is it still down to the engineer at the end of the day to do it manually?
Do you want me to take that, anybody? Or I'm happy to take it, unless Jamie and Rob, you have any comments? No, okay. So it's a good question. So when it comes to optimization, in the discussion, I was saying how it's great. You can have thousands of permutations and thousands of variables, and that's great. But as I've learned over the years, even in the likes of Formula One, there are limits to what people can make in sensible timescales. But you're right, taking that through to mainstream automotive, it's driven hugely by the manufacturing costs, production times, and feasibility. So the incorporation of manufacturing factors can be done. It's in itself, it's done through interaction with the engineer. But what you're doing is you're setting certain rules in terms of different types of material usage, different ways you can subdivide and break up your ply shapes that will evolve, because those subdivisions affect hugely the complexity of the lamina that you're going to create. So it's not an automated way to consider manufacturing, but it's set up in a way that your knowledge and experience can be fed into the optimization, such that you're not getting a design that's a basket case to make, which is vitally important.
Thank you.
Yeah,
okay.
I'd agree with that. So things like ply stacking sequences, minimum ply shapes, maximum laminate thicknesses, minimum laminate thicknesses, all these things we consider as sort of manufacturing constraints, and they can go into the optimization.
Thanks, Rob.
Thank you. I think Martin answered some of the questions in the last summary slide set there as well, which pointed the way. Thank you very much.
Great. Thanks, Alan.
Thank you, and thanks, Alan. We also have an anonymous question. I read to you. It's given the development lead time and change points to a volume passenger car program are very much longer, less infrequent than a motor racing program, where might the benefit for an OEM like Ford or JLR? So effectively, F1 is one spectrum. There is another spectrum of passenger car where can be the opportunity there for a longer term development type of car.
I think that's actually a good straightforward question. So because we've worked over the years with mainstream automotive suppliers, if they're looking at, take the example of a full body in white that's composite. Alan's obviously raised the important factors of manufacturing, but any type of structure like that, an automotive body has got so many requirements. In the modern engineering world, you've got your vehicle safety, your static and dynamic stiffness, attachment point stiffness. That there are so many requirements there, and being able to utilize the optimization technology on that platform allows it to really stretch its legs on the benefits, of considering those multiple attributes. And when you do that, I've got an example where we worked with a company, and the material usage of carbon in the chassis was reduced from 240 kilos. It was a fairly big, heavy carbon structure, down to 200 kilos. And that was absolutely a direct result of the optimization. And it considered the manufacturing, and that result went back into their development cycle. So it wasn't sort of a concept and could it work? It was actually used in the duration. And that in itself as a activity took 3 to 4 months. So it wasn't small and quick and magical. It was applying optimization to good digital engineering. But that amount of material usage on volume production is huge cost savings.
Thank you, Martin. Jamie, Robert, do you have any thought to share on those?
I think that the important thing just to consider is that it's always going to be applicable. It's just going to be different inputs and outputs. And like Mike says, on somebody that is mass producing something, they don't have to save much on each product to then multiply it up by tens of thousands of components to actually make the benefit.
Yeah, very true.
Yeah. And Martin, I think you also make a very direct connection with the aerospace before, or where you said that even a small saving there, and there is a long development time anyways there, then it has a very big impact in the overall system. So not only automotive, but also other sectors can benefit from this type of approach indeed. Conscious of the time, I think we we are at 11 o'clock. There are other questions coming through, but I think it's do we have time to answer one more, maybe?
Maybe one more if you want to.
There's one says, picking a typical use case such carbon monocoque, how much time would the process typically save in the product development process? So would you be able to quantify that one?
Ooh, that's a good question. Jamie's come off mute. Do you want to answer that, Jamie?
The thing I'd say is, given the fact that the sort of F1 development time scale is pretty much fixed, we know when the first race is, and we know when the last race is, and we know when we're going to start developing something. It might not save time, but it will allow more iterations and therefore give us a higher performing product at the end of the day.
Yeah. I think that's a very good answer. Engineers just work the time they've got, don't they? Particularly in motorsport. So yeah.
Yeah, that's indeed a good one.
Perfect.
Thank you. So now really, I think we came to the end of the webinar. So I just again like to thank Martin, Jamie, Robert for putting the slides together, going through the presentations, answering the questions, and above everything else, having successfully run this project, because it was a very interesting project to be part of. Well, as outsider ID, looking and monitoring the project, but I clearly see the benefit and the application, or not only in the automotive sector, but other sectors. Not only Formula 1 motorsport, really. So many thanks again to the attendees to ask the questions, and to you, Martin, again, Jamie and Robert, have worked hard to make this project successful.
Brilliant.
have to say that this was the first one of a series of 3 workshops. So there are going to be 2 more comings, one on Wave AI on the 6th of May, and another one on another project called Air Force on the 19th of May. More information will be on the link. So thanks again, everybody, and have a lovely day.
Brilliant. Thank you all. Thanks for watching.
Bye.
Take care.